delay. Yeah. A very warm welcome to this webinar organized by Material Science and Additive in Additive Manufacturing. So for this version or this edition of the webinar, we'll be covering the topic of data-driven process modeling and monitoring in metal additive manufacturing. So I would like to give a brief introduction to the journals for the people that are still unfamiliar with it. So Material Science in Additive Manufacturing is a relatively new journal, but also not that new in the field of additive manufacturing. So the journal was launched in 2022, and within 2 years, we are indexed in both the Web of Science under the Emerging Science Citation Index as well as Scopus. So in just this year, we have received our first impact factor of 4.6, which places us in Q2 of the engineering manufacturing category. For Scoopers, we are in Q1 with a site score of 6.1. So material science in additive manufacturing focus on the materials aspects in terms of additive manufacturing. And our final aim is to be one of the top journals in the field. So we require the support from the authors as well as the researchers working in this relevant area. So for today's webinar, we actually have two invited speakers covering the topic as mentioned previously. So to kick off the webinar, we will have Dr. Giulio Matera from Italy. He will be covering the topic of real-time process monitoring under small and unbalanced data conditions, specifically talking about wire arc additive manufacturing. And then we will have Prof. Lee Xiaopeng from the University of New South Wales, Australia, and he'll be talking about machine learning approach for the process structure property relationship. So maybe without further ado, I will hand over the presentation to Dr. Giulio, where he will start with his topic or his speech for today. Yeah,
For the presentation,
Dr. Giulio,
Professor
please.
Villa. May I share the screen, right? May I?
Yes, please go ahead.
Okay, thank you. Okay, just a quick check to let me know if everything it is fine and you can see the screen.
Yes, we can see your screen.
Okay, so I'm really thankful to be today here to present more or less my research line topic that is related to real-time process monitoring in additive manufacturing. And in particular, today we are going to speak about how to develop an application under small and unbalanced data condition. This is a really interesting topic, especially for the industry. We were working since years now with industrial partners that are interested in this topic. I mean, to try to understand if something is going wrong during the additive manufacturing process. And what they told us is that probably the main issue that they're incurring to develop application is not really related to the tools, but it's related to the data, because anytime that they are going to be able to collect data, these data are unbalanced. And for unbalanced, I mean that usually you are going to get plenty of data about good deposition, I mean deposition of materials that do not present any kind of defect, and you're going to have really few amount of data related to defect condition. So today we're going to develop an application together for wire cutting manufacturing to see in action the proposal and methodology that is, let me say, new in the field and really promising for industry perspective. Sorry. Okay, so as I told you, today we are going to discuss about wire arc additive manufacturing process. The wire arc additive manufacturing process is a metal additive manufacturing process based on the principle of welding. So essentially here we have a welding robot that is pre-programmed thanks to a CAM software because you have a CAD model, you're slicing the part, you are going to develop the program, the tool path for the robot, and then essentially layer by layer, you are going to turn on the welding torch and you are going to deposit welding beads one after another. And then before to reach the final part, you have to post-process the part to get, the final part that is compliant with, the finishing that you like to have for your product. Now, it is really interesting technology, especially for industry, because here you have a real low initial investment, because more or less the machine that you need to starting with when it costs you something like around $100,000, not more. There are a lot of materials that can be welded with the same technology. So this means that you have not to change any equipment, any part of your equipment to be able to print aluminum or steel or nickel-based alloy, for example. It is an energy efficient process because most of the power energy that you are supplying is converted in heat that at the end is going to melt the wire and to print the component. Here with this technology, you can have really high deposition rates because compared to powder bed fusion, you can have also 5-6 kilograms per hour of deposition rates. That is something incredible, right? And these allow you also to fabricate large scale components in a reasonable amount of time. And also because you are not limited by, the envelope of the powder based machine that you are using for additive manufacturing with powders. The only problem of when is that it's really prone to get a lot of defects inside the process. And not speaking only about porosity, that is something common also in laser based or powder based, let me say, additive manufacturing. But here you're going to get really rough surface. You can get easily humping problems, geometry deviation with respect to the path, distortion, that are going to make not useful your part to be used in a real uh, use case scenario. So process monitoring and consequently also the feedback process controls are two main factors that make this additive manufacturing process, let me say, usable for industry. So one of the topic of process monitoring is the ability to identify those anomalies as soon as they happen. Okay, because in this way you can correct the process with feedback control action, or you can stop the process and you can avoid to deposit material waste, material, and let me say energy. Now, when you are trying to monitor the wire arc additive manufacturing process, you can rely on really several kind of data sources. And what every data source allow you to detect potentially different kind of defects. So you can use welding signals, and I mean for welding signals, something like that, the welding current and welding voltage acquired to high sample frequencies to collect pull shift or arc shift that maybe can cause layer collapse, porosity, humping, other problem like sputter and the unstable heat input during the process. And as material scientists, all of you know how it is important to maintain a stable heat input during the process for stabilizing the thermal behavior of the metal and for the microstructure. And you can do it just monitoring this signal. You can use, however, also acoustic signals. And for acoustic signals, you can use microphone and acoustic emission sensor that are more like vibration style sensor, let me say, in which you are going to collect data not more at 5 kilohertz frequency, but much higher, like 100, 2000 or 500 kilohertz. And when you are going up with the sample frequency, you can detect stuff like hot cracks and porosity. And porosity, not only, let me say, big porosity, but also small porosity that happen during the solidification of the metal. But at the low heating, to the low sample frequency, you can also detect layer collapse and a stable heat input during the process. Because at the end of the day, as you can see here, there is a correlation between the acoustic emission shape that you are going to collect from the process and the welding signals like the current and the arc current, the arc voltage behavior. So you can see the correlation with the peaks, for example. Another kind of information or data that you can collect is definitely the welding images. So you can place a welding camera on your robot and you can collect to frequency above 30 hertz about what's going on inside the melting pool, and then here you can detect again sputter, layer collapse, and as well unstable heat input during the process. Now, if you can see here that you have really plenty of possibility, and sometimes you can go with just one data collection source to detect develop an anomaly detection or process monitoring application if you like, but you can also use also several kind of sensor together to develop something like multi-sensor fusion process monitoring application, and that's what is going to see today. What I'm going to show you today, how to develop a multi-sensor process application. Now, as you can see, the first problem is the frequency, data collection frequency, because if you are going to use arc voltage sensor and acoustic emission sensor, in one case you have 5 kilohertz data acquisition system or data collection and 100 kilohertz. So the first problem that you are going to include is how to manage this really different frequency of data collection. And then the second problem is that if you want to develop an online real-time process monitoring application, you have to define an application window. What this mean? This means that once you collected your data, you have to define the sample frequency of your application, let me say 1 Hertz. So do you want to have a feedback from the state of the process in terms of anomalies or defects every second, for example? So you're going to collect window from your signal, you're going to split in window of 1 second, and then you are going to use one sample of your machine learning algorithm, 1 second of the deposition. And from each window, that can be 1 second, it can be 10 seconds, it can be 100 milliseconds, it really doesn't matter. From this window, you have to extract features like meaningful information about the data that you see here, and then you can use these features as input to machine learning algorithms. So in time series, you have to define a window, but that's the same for images because you can process one image per time. So let me say you can have an application that works like one on 30 seconds, something like 330 milliseconds application, let me say, in which you are getting one image and you are feeding it to your machine learning model to, do this kind of defect classification stuff. Or you can use a stack of images, so a sequence of images, because you are considering the temporal relationship between the data, and then you are feeding inside your machine learning algorithm. Now, if you have a look about the state of the art in this field, you can technically use convolutional neural network to get images from your process and feed inside the neural network to get the class of your input. So you can associate to each image a label like it is an amping, it is a porosity or whatsoever. And that's let me say, the state of the art for image processing. But if you're thinking about the time series data processing, you're going to extract features from the data, and you can do it in time or in frequency domain or in time frequency domain. And then you are going to do the same stuff. Instead of feeding one image or a sequence of image, you are going to feed your machine learning algorithm with, let me say, a collection of features. And another interesting approach is that from time domain, you can, so from time domain like here, from a time series, you can transform this time series in the time frequency domain. So you can transform a time series in an image data, and you can use the same approach of image processing to process the spectrograms. That's the name of this transformation from the time domain to the time frequency domain representation. Now, supervised learning is more or less the state of the art. So you are going to get a sample, you have a prior knowledge about what is the meaning of this sample. So it means that you collect data, and then you are trying to mapping the input with the output. You are going to map your data with the label that you associate to that sample. But the supervised learning has several problems. The first one is you require large data set, and you require really extensive human annotation for training data. So you need to collect plenty of data, like thousands of seconds of deposition, and you have to, let me say, go to the microscope, cut all the specimens that you produced, and collect a label for each second of your data. And that's really time consuming. There is a lot of work behind it, and probably is the most, let me say, the big part of process monitoring application development. Then the coding part is the easiest one, let me say. Another problem of supervised learning is that it requires large data, as we said, but you need also balanced data. So this it means that if you have 1,100 samples of good deposition, you need 100 samples of porosity, 100 samples of humping, 100 samples of cracks to be able to develop a problem that is not biased by the unbalanced condition of the dataset. But the problem is that at the industry, as I told you before, they do not have this kind of massive datasets with balanced labels. So that's the first problem. And the second problem is that when you are going to define a training window, so you collect your data in some condition, when you are trying to use your machine learning algorithm outside your training data, such as here, you are going to have just random estimates. You do not have a really estimate an output that makes sense with respect to what you observed during the training procedure. So this means that if you are getting a new defect that you didn't take into account during the data collection, or an instability that happened in a different way with respect to what you observed, you are not able to detect it. Indeed, when you are going to use unsupervised learning, you have not to deal with this problem, because the main idea here is that it is possible to detect anomaly as deviations from the normal deposition data. So the only stuff that you need is normal deposition data. Now, why this is important from a certification perspective? Because if you have a look about the qualification procedure for welding processes, but it's the same for any kind of additive manufacturing process that is a special process under ISO standard, you need to weld or deposit, collect data, and test the mechanical properties and inspect the microstructure to inspect potential defects inside the part. And then if everything is working, you are going to qualify this parameter. Sorry. So this means that process monitoring is always something that happens with respect to the qualification procedure, because if you're going to have a look here, once you have a quality part, you are going to put this quality part in procedure specification, and then always you have to monitor your process with respect to the qualification procedure. So you have to be sure that what you are depositing, what you building up as an additive manufacturing part is building up in the same way that you observed during qualification procedure. And the data collection part, it's mandates by the ISO standards, is a really important data source for artificial intelligence. Because at the end, you can use the good deposition data that you collected during the qualification procedure and artificial intelligence for pattern recognition of good deposition data, and then just develop an application that is able to tell you if what you're building up is in line with what you observed during the qualification procedure. So you are monitoring versus the good deposition data. And here there are some references that you can use to have a bit more details about what I'm speaking. Now, what this means that once you have good deposition data, now the traditional monitoring approach rely on control charts. So you are going to monitor your process, you're going to save the information of your process, the behavior of your process during the qualification procedure. And then you are going to, at the end of the day, just consider one variable, for example, the mean value of the voltage, for example, and then you are going to establish a medium line, that's the mean value of your process in stable condition, and based on the standard deviation, so the variability that your process show you during the qualification procedure, you can define bounds in the called phase one of the control chart. Then when you are going to deposit the component, if this variable, the mean value of the voltage, is inside the control charts, it is okay, let me say. Otherwise, you have to go to, let me say, inspection of the part to stabilize if there is something wrong or not really in called, let me say, phase two. Now, what is the pro of the statistical process monitoring? And is because it relies only on good deposition data. And it is really something powerful for industry because they do not need to force defects in the data and then inspect and collect information. But the limitation at the same time is that it works only on 1D data. For example, mean on standard deviation value of the welding voltage or of the welding current, or let me say the power supplied during the process. Indeed, machine learning algorithms open let me say, the pathway for more complex, multivariate way to look to the data. And in this case, you can have like a reconstruction-based algorithm in which you are going to use a principal component analysis to transform in a low-dimensional space your good deposition data. And then once you learn the linear transformation that allow you to do it, you can use the inverse transformation to reconstruct the data. And if the data are the same that you use it to develop this weight matrix, this linear transformation, the reconstruction error is zero. Otherwise, if any deviation happens, the reconstruction error, when you are going to decode and then to encode and then decode the data, is going to be really high. That's the main idea. And another idea is the isolation forest, in which you can use several different trees to try to isolate all the data in your data set. And then when the data are really easy to isolate, they have a really high anomaly score. So once you build up your isolation forest with just a normal data, when a new data come out from the process, you are feeding it in the isolation forest machine learning algorithm, if it is going to be isolated immediately, it means that it's an anomalous condition. Because in both cases, it's like you are learning the pattern of normality in the data, and then you are using it to identify deviations. So based on this problem, I would like just to go to the conclusion of the presentation through an example. So think about to develop this component. Okay, you want to print this component. You have this machine with a voltage sensor and acoustic emission sensor. And the first step that you want to do is just trying several process parameters combination. Like here, you're going to identify if they are good or not, right? So you're going to deposit volts, as we saw before, with some strategies, you're going to collect information. Now, the problem is that at the end of the qualification procedure, you have a really strong imbalance because you have 70% of the data that you collected. And in this case, let me say all the samples, every 1 second of deposition that you collected in these cases, 70% of them are related to good deposition data and just the 30% of defects or anomalous condition. So this means that it's really hard to develop a supervised machine learning algorithm to do the process monitoring in this case. But what you can do is use all this information to develop a model, as Professor Leder is discussing, right, with the process modeling activity. You can use the process parameters and the output to estimate the layer geometry, the power consumption, the quality. And with this model that you are able to develop, as you have in the next presentation, you can write down and visualize process maps, and you can go inside process maps, identify best parameters condition, based on your specific goal. And you can do it only because you have a model, a data-driven model of your process. And then you are going to deposit. When you're going to deposit the machine, you are going to investigate the quality. This is a training wall without defects. Then you can, let me say, force some anomalies like missing gas or incorrect process parameters during the deposition that can happen during a real process. And then you can collect the data for testing purpose for both normal deposition and both, also abnormal deposition with defects. And then you can develop your machine learning approach. Now, for statistical process monitoring approach, you can collect the welding voltage. You can evaluate the mean for each second of deposition, and then you're going to define the upper and the lower bounds, like in this control chart. And then you are using the control chart's limits for monitoring. In a machine learning approach, what you can do, you can go to frequency-informed convolutional autoencoder for automatic frequency domain extraction from time series of welding voltage, and you can use another model in parallel to extract features from spectrograms, so from the 2D representation of this high frequency time series. And you can concatenate the feature extracted here and go through a machine learning algorithm. And here you can see how today is the state of the art, a really advanced application rely on stacking all together different kind of application of deep learning and machine learning. So here a bit of code. So you are going to get the high frequency data. You're going to convert them in spectrograms, and you're going to design an autoencoder with PyTorch. That's the code. So if you are going to save the video of this webinar, you're going to have also this image useful for coding stuff, but you can reach me on email and I can share with you the codes. And you can design a symmetric convolutional autoencoder for extract the latent space, so the features. And you're going to train it to reduce the reconstruction error. And that's how, from a coding perspective, you have to write it down. Okay. And then once you collected the latent space, from the latent space, you can get the mean and also the standard deviation and also other metrics like kurtosis skewness. Then for the frequency form, the convolutional autoencoder is something really similar. So you have here the structure, and here you have a bit of code with 1D convolution instead of 2D convolution to do the same job with, the frequency regularization terms. But if you are interested in more like coding and development side, you can rely on these slides or to these papers that you can find online. And then once you collect these latent spaces, you can concatenate together, and then you can feed, these statistics extracted from latent spaces, so like in the mean standard deviation, kurtosis skewness, and you can normalize them in a way that the scale of the both variables is going to be in the same range of 0, 1, for example. You are going to concatenate them, and you are going to feed inside the isolation forest. And now you're using isolation forest just to learn the pattern of normality in your data. So you are training it with, the good deposition, and you are testing with a mix of few good and bad deposition data with defects. And then I compared the results with statistical process monitoring. And you can see here that the difference is that you are going to reduce the false positive, but the most important, you are going to reduce the number of false normal, or the number of missed anomalies. You're going to reduce this number. So it means that during the monitoring, you are going to miss less anomalies that are control chart. And that's really interesting. So what you can do at the end, you can print the component based on all the stuff that we developed. Let me say on this stuff, right? We developed and tested our quality monitoring application on wall structure that are pretty simple. And then you can deploy and see in action your feedback control, your monitoring application that at the end can be translated to a quality index that tell you how good is the part that you are printing. And for example, when the quality index that you can compute based on the anomaly detection output is below a threshold like 0.8, you can employ corrective action to reestablish the normality of your process. And this means that you are going to be able to always print something that at the end is certificate compliant and technically can be used for the usage. And maybe you can skip from an additional qualification, non-destructive qualification inspection loop. Now, I took more or less 30 minutes for my presentation, so I have to conclude, but I'm really open to questions to discuss more about the stuff. So the conclusion is that most of the combination of reasonable plus parameters that you can use in additive manufacturing led in good quality deposition. And if you are in additive manufacturing side, you know that this is true. And another stuff is that probably I wanted to remark is that supervised learning struggles when dealing with unbalanced data set. So this means that at the end of the day, you have to force using process parameters that are not reasonable to get information about defects. And this makes no sense, especially for industrial partner. For us, in research perspective, it can make sense to show down the application, the potentiality of an application, but for an industrial setup, it makes no sense. And for real time, another stuff that I want to remark is that when you are moving to real-time process monitoring, it's really important to define application window. If you want to monitor your process every second, every image, every 100 milliseconds, and whatsoever. And then to develop a real-time application from each application window, you have to extract features. And let me say there are statistical descriptors of time and frequency analysis, the outcomes from the time and frequency analysis. And then another stuff that I wanted to remark is that you can use deep learning not only for supervised learning mapping, but you can use also for automatic feature extraction from your data. And then you can use this semi-supervised machine learning approach in which the only class that you know is the good deposition, right? That's why it is called semi-supervised, because you are in some way supervised the training with just one class data. And these semi-supervised machine learning algorithms outperform the statistical process monitoring control charts because they are able to detect more difficult anomalies with respect to control charts. And then we can use all this stuff together for certification-driven application. So AI nowadays may really represent a tool to improve the qualification procedure. The only problem is that all the stuff that I told you today, they lack a bit of explainability, and this limit really a bit their application for qualification process into qualification process. And other stuff that limited its application and qualification process is the definition of what is a reasonable threshold for the performance that you have to declare for your machine learning algorithm to be reasonable use to be used in a certification purposes. So in the ISO standards, is a topic that is not discussed. So technically, you cannot use statistical process monitoring, we saw, because the performance are technically low, but you can improve now the performances with respect to control charts. But now we have to speak with people of standards to develop a sort of threshold that we have to define to make it applicable for industry. So I would like to thank you, everyone, for the attention. That's here my email. If you want to reach me for asking question and material about the webinar of the presentation, and I will thanks all the editorial boarding of material science and additive manufacturing, my colleagues to give me the space to discuss about my research stuff today.
Yeah,
Thank you.
thank you so much. Thank you so much, Dr. Gillian. Yeah, we have some time for questions. So if you have any questions, feel free to raise your virtual hand and unmute yourself. I actually have a question in the chat box. Maybe I will repeat out the question for the rest of the audience. So how do you manage the latency while collecting the data? And the second part of the question is, do you map the process parameters data and image data? If yes, how do you do that?
Okay, for the first question, that's a really important topic, the latency. But if you think about it, when you are going to deploy on a real system an application, you can use multi-threading of you, of your CPU, and you can use one thread for the computation of the output of the anomaly detection and one thread in parallel to collecting data. So you have not really a problem of latency. The only problem is that you have to be sure that the time needed to get an output from your machine learning algorithm is below than your application window. So that's really a smart and interesting question, good point. And the answer is that it's a requirement for your application window decision. So, Amam, I don't know if I answered to your first question. Maybe you can reply in chat if you like, or you can open the microphone.
Yeah, I got your point.
Okay,
Yeah,
makes sense for
yeah,
you? Okay, because that's what I used to do.
okay,
Then the second, map the process parameters data to image. No, in reality, I mean, I don't know if we have time, Professor Swilong.
Yes,
Do we have
yes, we
time?
do.
Okay, so I want just came back to the
okay,
slides because after there is going to be the presentation of my colleague from University of New South Wales. Is going to discuss in detail about data-driven modeling. But the idea here is that here you have your process parameters, right? The
yeah,
wire feed speed, the voltage, the reference voltage in welding, and the welding speed. But it can be anything from additive manufacturing perspective. Here you have some variables like the layer height and the layer width. You collect information about the specific energy consumption, and you can use a regression model to map this continuous variable to other continuous variable, like a linear regression.
okay,
And then you can use also quality, other like binary classifier to get also some quality feedback. So here is an ensemble of machine learning models. Let me say again, some regression, some classification that are working on this tabular data. Now, once you have the output and you have the input, you can develop the response map. I'm going to write you in the chat.
okay,
Wait. I'm going to write in the chat surface response maps. And the surface response maps are just a visual representation of the input-output relationship of your data. But you have not to develop an image from the data. You have to get the input, the output, and you are using those to create surface maps.
Okay.
If we have time, I can share the screen with a bit of code. Professor Wilong, if you allow me,
Oh, yeah, sure.
and if it makes sense, of
Mhm.
course, with respect to the webinar. I don't
Yeah,
know.
sure. No
It's for
problem.
Amam, you know.
Yeah, no
Amam, do
problem.
you like if I'm going to open the Visual Studio to sharing the code to show you a bit what I mean better?
Yeah, please.
Okay. I'm going to just open. Okay. Okay. To think about it, you have your input, the X, right? You have your output, the Y.
Yeah.
Then, for example, you're using a polynomial regression to map the input with the output, right? With fit, stuff, linear regression, fit. So you are going to define a polynomial regression.
Yeah.
And then when you have more or less good results for your polynomial regression, what you can do is like create an X vector for your input. Because if you think about the input, you have just some data points.
Yes.
So you have, for example, let me say 0, 5, 20. And what you're going to do in the range is you're going to create 1, 2, 3, 11, 19, 20, right?
Yeah.
So you are going to create fake inputs that you are going to use to feed in your polynomial regression. And then when you see, you're going to create these grid points because you're going to do it for X, for this variable, this other variable. Then you're going to get the output from your polynomial regression.
Okay.
And then you're going to plot in the map X, Y, and the value of the polynomial regression is the color of the map.
Got
In
it.
this way, you are going to create nice map of your process, and then you can optimize because, for example, you want to go in the field where the specific energy consumption is lower. So you can go here and you can identify, some combination like 20 volt to wide field speed, for example.
Okay. I have one last question. Like, you are.
Did I share the screen? Wait.
No, you didn't share the screen actually.
Bloody hell, sorry.
But no problem. I understand. It was very
No, but
nice presentation.
thank you. But I don't know if I'm so sorry.
No
I'm so
problem.
sorry.
I have one last question. Like, how did you validate your machine learning model?
Okay, so what I did once I optimized the process parameters,
Yeah.
I used to print just one wall that in the wire arcade manufacturing field is, let me say, the structure used for material characterization perspective,
Yeah.
for mechanical properties and whatsoever. So I print one wall
Yeah.
with the optimized parameters. Then I collected the data of the optimized, so without defects. I
Okay.
inspected the wall and I trained the algorithm. Then I printed another wall with the same process parameters.
Okay.
So technically the data were the same, the welding voltage, the welding
Yeah.
current, or close by, but I forced during the printing of the wall some anomalies. Like, for
Okay.
example, I introduced some increment of the contact tip distance, or I reduced the gas flow rate,
Got it.
and I introduced some instabilities and I collected data about them.
Got it.
Thank you for the questions.
Yeah. Thanks. It was very nice research.
Cheers, buddy. Thanks to you.
Thank you. Thank you very much. Thank you for the discussion and thank you for the insightful presentation. let me go back to
Thank you.
my
Thank you,
slide.
Professor Minor.
Yeah, thank you so much. Yeah, so um let me sorry. Yeah. So unfortunately Prof Lee will not be able to join us today because his flight back home was delayed. So what we will do is that we will have a recording of his presentation and we'll be posting it onto our journal website. So do look out for that for his presentation. So before I end today's seminar, I would like to use this opportunity to do some promotion for our new journal, Engineering Science and Additive Manufacturing, that covers the other aspect of additive manufacturing. We do know that material science, material development is an active topic, especially for additive manufacturing. But on the other aspect, we are also having new techniques like in-process monitoring, machine learning applications in this aspect of additive manufacturing. So I do look forward for your support for our new journals, Engineering, Science and Additive Manufacturing. And finally, we'll be hosting our second edition of the International Conference on Future of AM in Singapore next year in August of 2026. So the website stated there is already live and we are already open for abstract submission as well as registration. So do support the journal and I look forward to meeting you all in Singapore. So for the first edition that we had this year, we have quite a well attended conference of around 300 presentations from 18 countries. We are also giving out posters and presenters awards to the students as well. So I look forward to meeting you all in Singapore or somewhere else along across the world in the near future. So with that, I will end the webinar for today. So do continue to engage us through material science in additive manufacturing or through engineering science in additive manufacturing. Yeah, so we look forward to um your support with that. I wish you all a good day ahead and I see you all at the next webinar that we will be hosting soon. Yeah, thank you so much. Bye bye.
Bye bye. Thank you to everyone. Bye bye.
Thank you. Bye bye.